Hi everyone! In this video, I would like to demonstrate a shader that reacts to mouse clicks and movements. It's a variation of a shader displaying the Mandelbrot set, which I created about a year ago. This time, however, we will enhance it by adding the Julia set at a point chosen by the user, and we will add more control elements, all of which will be controlled by the mouse. So let's get started. Okay, we'll start by creating a new scene with a colorect, but this time I'll set the dimensions to 1920 by 1080, which is a full HD resolution, so we can better observe the results. Otherwise, it's the standard process of creating a shader material, etc. So right-click, create new scene, let's call it Julia. Okay, right-click, add child node. Correct. And now, as I said, the layout transform size I'll set to 1920 by 1080 and scroll down, material, create a new shader material, click, create a new shader, which is called julia.gg shader of the canvas item type, and I'll put it to the shaders folder, create, and click again to open it in the shader editor. Let me just zoom out a little bit and let's remove everything that isn't needed so that only the fragment function remains, deleting vertex and deleting light. Okay, so this time I won't go into detail about the mathematical background of the Mandelbrot and Julia sets because this tutorial is mainly focused on working with mouse events and handling them in shader code. If you're interested in the details of the fractals used, I recommend watching the video on creating the Mandelbrot set, which I linked in the description of this video. So let's jump straight into coding. As is well known, both the Mandelbrot and Julia sets are based on iterations of a quadratic function in the complex number domain. Therefore, we need to set a maximum number of iterations to ensure that the computation does not repeat indefinitely. To achieve this, we will define the following constant. Const int for integer max iterations, and let's set it to 2000. Okay, next we will set up the following uniform parameters. Uniform. Okay, it seems like Godot wants it before the constant, so uniform vec2 resolution is vec2 1920 by 1080. Okay, this is our standard parameter to recalculate the aspect ratio. Now we need a zoom factor because we will want to zoom in and out the resulting fractal with a hint range and initial value, let's say 2.5. Okay, and let's set the range from 0.1 to 10 with the step 0.01. Okay, then we will need to pass the current mouse cursor coordinates. It will be vector2, let's call it mouse, and let's set the initial value to the 0 vector. All right, and finally we need to distinguish between the situation where the mouse is clicked or it's not clicked. So it will be a boolean called clicked and the initial value is false. Okay, in the video about the Mandelbrot set, I explained the following function, which we'll use to calculate iterations for individual pixels. Simply put, it's an interpretation of this complex function in Godot shading language, so I'll just write it here. Right before the fragment function, so float get iterations with parameters vec2 z, and vec2c, as we could have just seen them in the quadratic function. Okay, and now the iterating. Float iteration starts at 0, and we at the end want to return the number of iterations, which will determine the color of the particular pixel. And now the iteration itself, for int I from 0, I less than max iterations, I plus plus, and that is the result of vector 2 zx times zx minus zy times zy. So we are simply putting this complex number, this vector, to the power of 2 and 2 times zx times zy. Okay, and increase by the c constant. Very well, and now we need to determine if we exceeded some kind of boundary or not. So if dot z, it is basically the length to the power of 2, so it is supposed to be a bit faster than just computing the length, which involves square roots, is greater than 4, then we can break the cycle. Okay, and otherwise let's increase the number of iterations plus plus. Okay, I'll just show more of that. So this is the function. With that, the preparatory work is done, and we can move on to the fragment function. So first, we will shift the origin to the center by subtracting 0.5 from the UV coordinates, and then we'll adjust the aspect ratio to ensure that the resulting fractal shapes are not stretched horizontally. Okay, so let's edit the fragment function, and as I said, vec2 UV is UV minus 0.5, moving the origin to the center and recalculating the aspect ratio. UVX is multiplied by resolution X divided by resolution Y. Okay, now we need to perform the iteration calculation. For the Mandelbrot set, the initial value is set to a 0 vector, and for the constant c, we will use UV coordinates of the current pixel, like this. Float iterations is the result of getIterations function, and as I said, for the z, we start at 0 vector, and for c, it's UV. And since we are working with zooming in and out, let's multiply the UV by the zoom factor. All right, I will just add the node Mandelbrot, so we can then easily distinguish that from Julia. All right, now we need to color the resulting value by normalizing the final iteration count to a range of 0 to 1 and multiplying it by a color, for example, red. So that would be vec4 color is, and now iterations divided by the max number, so float max iterations, and multiply the result by a red color, which is simply 1 for red, 0 for green, 0 for blue, and 1 for alpha. This time I'm using vector 4. So we get colors in RGBA format, because later we'll want to overlay the Mandelbrot set with Julia set and use the alpha channel to still see both, to see through them. Now we just need to assign the color to the internal variable color. So color is color. Wait for it. Okay, let me just show all of it. So we have our familiar Mandelbrot set, but that's just the beginning, and now we'll finally get to the main point of this tutorial, displaying the Julia set based on mouse clicks coordinates. First, I'll finish writing the rest of the shader code, and then I'll create a GD script to handle the corresponding interactions. For the Julia set, we'll calculate it at specific coordinates, so the initial value is set to the UV coordinates. In contrast, the constant C will actually be constant this time, and we will assign it a value based on where we click with the mouse. To achieve this, we created a uniform parameter mouse at the beginning, which will contain the coordinates from the mouse events obtained in the GD script. These coordinates will be set according to the dimensions of our color rect, so x will be in the range of 0 to 1919 and y in the range from 0 to 1079. To normalize them to the UV coordinates used in the shader, we just need to divide this vector by the resolution vector. And of course, we subtract 0.5 again to center the coordinates and recalculate the aspect ratio. Okay, let's just put it here right after the definition of UV coordinates in the fragment function. So vec2c is, as I said, mouse divided by resolution, and we subtract 0.5. Okay, and of course we need to recalculate the aspect ratio as well. So Cx is multiplied by resolution x divided by resolution y. Okay, now for the Julia set calculation, we will use the UV coordinates as the initial value, then the obtained value C as the constant, and color the result white with an alpha value set to 0.5 so that we can still see the red Mandelbrot set underneath. Let's place this after the definition of color, so which would be here, and then we can blend the new color into it. So we want to do it only if we click the mouse at some specific coordinate. So if clicked, then again we will call this and get a new set of iterations. This time we name it Julia. And as I said, it doesn't start at 0 vector, but at UV coordinates. And we are not working with UV coordinates here, but with the C constant. All right, this is the difference between Mandelbrot and Julia. And now let's add it to the color. And it will be like this, copy, paste, but we are increasing. And the color isn't red, but it's white, red, green, blue, all set to 1, and the alpha value, let's set to 0.5. Okay, now we have the shader code, and we will continue by creating a GD script to control these parameters. So I'll add the script and create a reference to the color rect in it. So in the scene tree, I select the root node and click this icon to create julia.gd script, create. Here it's opened, and as I said, we need a reference to color rect. So I'll just drag it holding the control key and release, and we have this onReady declaration right here. All right, in the ready function, we will add the initial setup of the shader parameters that we want to change later. So it would be this. We need a color rect and its material property, and now set shader parameter, and the parameter is, as we know, mouse, and let's start at 0 vector 2. Okay, and then we have the parameter clicked. Let me just copy paste, and it's clicked, and we start at false. Nothing is being clicked. Okay, very well. Now let's finally handle the input using the input function. So instead of process, which we don't need, I will implement func underscore input. Okay, and We could also use unhandled input instead of this, but since we don't plan to create any UI that would capture events, it's fine to use input in this case. And we'll also add the ability to exit the program with the escape key, because we'll be running and stopping the script multiple times. So let's start with that. If input is action just pressed, and we will use the standard action UI cancel, which is by default mapped to the escape key. Then let's get out of this program. Get 3, quit. Okay, we can try it out, so I'll execute the scene. We should see the Mandelbrot set, and now when I press escape key, we are out of that. Great. Now, let's handle the mouse events. The first thing we want is for the Julia set to appear at the clicked point of the Mandelbrot set. So we need to send a new value for the mouse parameter to the shader. We'll do this like this, and we will handle only the left button. So let's continue right here. If event is input event mouse button, where is it? Here, and event button index is mouse button left, so we are handling only the left button, and event pressed is set to true. If we don't do this, we would be handling the mouse release as well, and sorry, double equals, of course. Okay, so in this case, let's again set the mouse coordinates. I'll copy this line and paste it here, but this time we are not using the 0 vector, but we'll take position from the event. So event position. All right, this is the first one, and now we need to, of course, tell the shader that we are clicking. So let's set clicked to true. Otherwise, else, we are setting click to false, back to false. Okay, now when we run the scene and click with the mouse, we'll see the Julia set as long as the mouse button is held down. Let's try it out. Okay, click. This is too big, I guess, but it works, of course. And right away, we can see that the set is too large. So we'll go back to the shader code and set a fixed zoom for it, like 2.5. So here in the iteration, we are working with UV for the Julia set, and let's change it to UV times 0.5. Let's check it out again. Click. Okay, I guess that's much better. Alright, however, it would be even better if the set were displayed when we hold down the left mouse button and move the mouse. As you could have seen, I've been moving the mouse and the set just kept disappearing. So we'll improve our script like this. This is the first condition, and we'll add the second one. Or, and let's continue on the next row, event is this time we are working with the movement, so it would be input event mouse motion. Where is it? I don't see it in the code completion. Let's just write it, input event mouse motion here. Okay, and event. This time, this kind of event isn't using button index, but button mask. So button mask is, and again, mouse button left. Okay. Now, when I start it again, what exactly is wrong? Event is input event mouse button, and mouse event is not defined in the event, not event, sorry, event. Now let's try it out. I click and drag, and now it works perfectly. We can see how smooth it is. And notice that the most interesting shapes appear when we move along the edge of the Mandelbrot set, like this one or this one. which beautifully demonstrate its fractal nature. Okay, let's end the program. We are basically done. But what if we improve the scene a bit more? Right now, we are only using the left mouse button, which is a bit limiting. Let's do this. With the right mouse button, we will move the origin of the coordinates, and with the mouse wheel, we'll change the zoom. Then we'll be able to focus on some edge cases and get even more interesting patterns. But before we dive into that, let's add one more improvement to make it easier to focus on those edge values. We will add something like a crosshair made up of two thin lines, which we can best achieve using the smooth step function, like this. Let's get back to the shader code. And here, after calculating the Julia set, let's calculate the crosshair. Alright, so as I said, two smooth step functions. Color would be multiplied by smooth step and the edges, let's set very close to each other from 0 to 0.001, and the value is absolute value of UVX minus CX. Okay, this is the standard way to generate a thin line. This is the first one, and now the perpendicular one, which will be the same, but this time we are working with the y coordinate. Y and CY. Okay, and when we run the scene, and click, we can see the crosshair as it nicely follows the mouse cursor when the left mouse is held down. Okay, now let's move on to the zoom. Everything is set up in the code as we have the zoom parameter here, and we already use it in the code. So we'll just improve the GD script. We'll add a zoom parameter, use it for the initial setup in the ready function, and then capture mouse wheel events in the input function. To avoid infinite zooming, we'll limit its values using the move toward function. So I'll start by adding the zoom variable, where zoom starts at, as we know, 2.5. Now let's use it in the ready function as a new line. So we are setting the parameter zoom with the value zoom, and let's implement it in the input function. So this time, if event is input event mouse button and event button index is mouse button wheel up. Yeah, this one. Mouse button wheel up. This is the mouse wheel. Then let's change the zoom factor. Zoom is, and as I said, we'll use move toward, so we'll make sure that it won't exceed the final set value. So from zoom to, let's say, 0.1, and the step would be 0.01. Okay. And again, we need to change the parameters. So this time we are changing zoom. Let's copy paste. And yeah, I think that's all we need to do here. And now let's do the same for wheel down. So copy paste, wheel down, and we are moving in the opposite direction. So we'll increase the zoom factor up to 10. Okay, that should be it. Let's run the scene and try using the mouse wheel. Executing, and now moving up, moving down. Great, seems to be working. Escape. And now let's implement moving with the right mouse button. First, we'll add a new uniform parameter to the shader. So this is the shader code, and let's add it here. So uniform vec2, call it shift, and again, let's start at the 0 vector, so there is no shift. And now we'll subtract this vector from the definition of UV and C in the fragment function. Here it is, so UV minus 0.5 minus shift, and let's do the same for the C. So this minus 0.5 minus shift. Okay, and in the GD script, we'll add a shift parameter, set its initial value, and then send it to the shader. And we'll also need to account for the zoom factor. So here, var shift starts at just a 0 vector. And in the function ready, let's copy, paste, and use shift and shift. All right, and in the input function, let's continue at the end. So if event is input event mouse motion, because we'll be just dragging with the mouse. So input event mouse motion, and event, again, button mask, not button index, is mouse button right, this one. Then we will change the shift. Shift is increased by, and now we take event relative, which is the direction we made with the mouse. And this is usually a unit vector, so adding 1 in each direction would be too much. We need to divide it by, let's say, 1000. So multiplying by 0.001 and divide by the zoom factor. So it just takes it into account and shifts accordingly. And of course, let's set the new parameter to the shader. This. Okay, let's run it again and test the panning. So I click, and now I click the right button and hold it and drag. Seems to be working pretty fine. Let's just move it here and show some Julia set, and we can see it seems to be shifted along with the Mandelbrot set. We would like to fix that. So let's get out of there. And to prevent this, we'll isolate its coordinates into a separate vector. So let's say JUV for the Julia set. So here, vec2 JUV is just like UV minus 0.5, but we are not subtracting the shift this time, just this. Okay, and let's fix the aspect ratio. Copy and paste and make it JUV. Okay, and now in this clicked block, we need to use, instead of UV, just JUV for the Julia set. Let's try it out. Okay, clicking, increasing the zoom factor, moving, and now click, and it's perfect. We can just work with anything, increase, zoom in some interesting parts. Yeah, this is it. This is perfect. By the way, maybe the zooming could be still improved when the origin is shifted. As you can see, it's still taking the 0, into account, but we'll leave that for another time. We can say that we are done. What happens if I, for example, try out this bottom part? Okay, another interesting shape. Or this island. Now it's very thin. Very well. Thank you so much for watching. In the same way, we could capture keys from the keyboard or game controller and send all such events to the shader for further modifications of what it should display. This was a basic example, but we've clearly shown how simple and straightforward the whole process is. So once again, thank you, take care, good luck with your projects, and I'll see you next time.